Welcome. I am Dr. Ravi, working as Assistant Professor in the Department of Pharmaceutical Engineering, BVIT Narsapur. Now, I would like to teach on the subject Chemical and Process Thermodynamics. In that, today I discuss introduction. Before going to course content, first we discuss on the course objectives. In this subject, in the first unit, we are going to learn basic thermodynamic properties like heat, work and entropy. In the second unit, we are going to learn pure compound properties, how to determine the pure compound properties and how to develop the correlation among them. In the third unit, we are going to learn how to determine the mixture properties and how to develop the correlations among them in the mixture. In the fourth unit, we are going to understand what is the phase equilibrium and how to develop it or how to achieve it, and how to inhibit it. In the fifth unit, we are going to learn chemical reaction equilibrium for homogeneous and heterogeneous reactions. So, in that, we are going to see how to develop the chemical reaction equilibrium. If you don't require, how to inhibit it. So, what are the properties we need to inhibit it? So these are this subject objectives. So, the course outcomes, what are the objectives we have seen? So, the student is able to understand about all these objectives after the completion of the every unit. This is a course mapping between the course outcomes and program outcomes. And here I am following the two textbooks, that is Smith and Vaness, Introduction to Chemical Engineering Thermodynamics. Next one is a K.V. Narayana. It is an Indian author-based textbook, Chemical Engineering Thermodynamics. Before going into the content of the this chemical and process thermodynamics, first we will see what is the thermodynamics. The steam engine was born in the 19th century. The steam engine was developed in the 19th century. Later they want to understand what is the efficiency of this steam engine and what are the limits of this steam engine. So that to understand that, based on the few principles or laws, they developed one science that is called thermodynamics. So, those laws are zeroth law of thermodynamics, first law of thermodynamics, second law of thermodynamics and third law of thermodynamics. Now, here we will see briefly about these laws. What is the zeroth law of thermodynamics? For example, two systems are in a thermal equilibrium each other with a third system. Then these two systems are also each other are in a thermal equilibrium. That is the zeroth law of thermodynamics says. Next one is the first law of thermodynamics. First law of thermodynamics is also known as the law of conservation of energy. This first law of thermodynamics says the total energy of an isolated system is constant with the time progression. Therefore, the energy cannot be created and cannot be destroyed, but the energy can change from one phase to another phase, or one form to another form. This is the first law of thermodynamics. Next one, second law of thermodynamics. In the second law of thermodynamics is explained or developed based on the one entity, that is entropy. Entropy, and what is the meaning of entropy? Means it is a measure of disorder and randomness of the system. So the second law of thermodynamics says this randomness and disorder of an isolated system is continuously increases with the time progression. And not only that, this second law of thermodynamics is also based on two postulates. Those are, this law also suggests that heat will spontaneously flow from high region of temperature to low region of temperature. This is the first postulate. Second one is and that it is impossible to convert heat completely into work with a 100% efficiency in a cyclic process. These are the two postulates. Other words, these two postulates can be explained like this also. No device is available to transfer heat from low temperature to high temperature. Second postulate is no process is available that can convert the heat energy into 100% work energy. Next one is the third law of thermodynamics. The third law of thermodynamics states that as the temperature of a system approaches absolute zero, the entropy of the system approaches minimum value. Generally, according to the second law of thermodynamics, the entropy of an isolated system continuously increases with the progression of time. But the third law of thermodynamics says the entropy of any particular system can be minimized or it won't increases with the progression of time when it reaches to the 0 Kelvin temperature. Next one. This thermodynamics has a lot of application in various fields, in the mechanical department, in a civil engineering department, in electrical engineering department, electronics engineering department. So means this thermodynamics has a many application in various disciplines. So here, what are the applications of thermodynamics in a pharmaceutical engineering? It determines what is the heat energy required for if you want to do any particular work, and it also deals about the direction of the process. What direction, if any chemical reaction, when A plus B gives rise to C and also gives rise to D also. So in that circumstance, in this condition, this reaction is which direction it can move, that can be explained by the thermodynamics. It also develops the correlation between the properties of the system. It is also determines it is helpful to determine the phase equilibrium and reaction equilibrium. Now we come to the first unit content. In first unit, we have this content: the types of energy, work, heat, energy changes, applications of first law to different processes, entropy, second law of thermodynamics and its applications, reversible and irreversible process, Carnot cycle, TS diagram, enthalpy of mixing and disorder, refrigeration and liquefaction. So with this, the first unit can be completed with these topics. First one, types of energy. Generally, in the universe, various types of energies are there, but these energies can be classified into kinetic energy or potential energy. Kinetic energy associated with the motion of the bodies. Kinetic energy associated with the position or state. The kinetic energy examples are mechanical energy, thermal energy, electrical energy, sound energy and radiant energy. Potential energy examples are gravitational potential energy, elastic potential energy and chemical potential energy. Now we will see briefly about these energies. First one is mechanical energy. Mechanical energy is associated with the motion of mechanical body. For example, the motion of the pendulum or motion of the hammer. These are the examples. Thermal energy. Thermal energy is associated with the movement of molecules. It is also known as heat energy. Electrical energy is associated with the flow of electric charge. Next one is the sound energy. Sound energy is associated with the vibration of particles in a medium. Radiant or electromagnetic energy. The radiant or electromagnetic energy is associated with the electromagnetic waves. Next one is the examples of potential energy. In that, first one is the gravitational potential energy. Gravitational potential energy is associated with the gravitational field, the state of gravitational field. Next one is the elastic potential energy. Elastic potential energy is associated with the stretching and compression of a body. Next one is the chemical potential energy. Chemical potential energy is associated with the chemical bonds. So with this, we can conclude these are the types of energy, and these types of energy are classified into kinetic energy or potential energy. The next topic is work. Generally, by physics definition, work is equal to the force is exerted on a particular body, and that when the force is exerted on a particular body, when that force is creating a displacement in that body, then you can say some work has done. So that is the according to the physics definition. So means the work is defined as the product of the force applied to an object and displacement of the object in the direction of the force. So the formula for that dW is equal to F into dz. This is the definition according to the physics. But then how this definition or how this work is applicable to thermodynamics? So in thermodynamics, if you want to determine what is the work of a engine, so it is determined based on the what is the work done by the fluid or fuel or gas on a piston. Okay. So when the fuel is enter into the cylinder, it is exerted a force on the piston, and that is creating a displacement in the piston. So that is a work. So what is the formula for that? How to determine the formula of work done by the fluid in the cylinder? So to determine that, we know pressure is equal to force by A, force by cross sectional area. So from there we can know what is the force exerted on a piston by the fluid is equal to the pressure of the fluid into cross sectional area of the piston. Now, what is the displacement? So from there we got the F. Now, according to the previous definition, dW is equal to F. F you got. Now, what is the dz? So to determine the dz, so what is the displacement in the piston? That is equal to what is the expansion of the fluid. So the expansion of the fluid, that is dV is equal to how much dz in the z direction, how much it is expanded into cross sectional area. So from there we can write what is the dz is equal to dV by A. So now we know what is the F is equal to. Now from here we know what is the dz is equal. Now we can substitute in that formula, that is equal to dW is equal to F into dz. In that here F is equal to P into A into dV by A. Okay. So from there the A and both get cancelled. Now dW is equal to P into dV. Now integrate on both sides. Then so the integration limits for the dW G0 to W, and next side the integration limits are V1 to V2. So when you integrate the dw, will get the w. When you apply the limits also, will get the w only. So next one, when you integrate this p into dv, that is, we'll get the integration of the dv is equal to v. Integration of the dv is equal to v. Now from here, w is equal to p into v. Apply the limits v1, v2. From here, w is equal to p into, apply the limits v2 minus v1. So this is the work done by the fluid in the cylinder on the piston. Next one is the heat. So heat is a form of energy. So it can be transferred from high temperature region to low temperature regions. Heat is manifested only during the change of state of a system. When the this heat is manifested when any system is changing its state, then only that heat can be manifested. Like work, heat has also same units like joules. Next one is the energy changes. Energy is a quantity, so that can be stored in the system, or it can be transferred from the system to surroundings. So what is the system first? System is where is our interest, where we want to study on that particular subject. So that is called system. Surrounding means what are the things which are adjacent to the system are called surroundings. For example, we are considering this is a system, means our interest is we want to study the thermodynamic changes in this system. Then surroundings are the whatever the things are there surrounded by, means this universe also can be considered as a surrounding. So when the energy is stored in within the system, it is stored in form of internal energy. But when it is transferred from the system to surroundings, it transferred as heat or work. Next one is the applications of first law of thermodynamics. We have seen what is the first law. First law is it is also known as the law of conservation of energy. So from the definition, the first law of thermodynamics, the total energy of an isolated system constant with the time progression. Therefore, the energy cannot be created, cannot be destroyed, but the energy can change from one form to another form. That is a first law of thermodynamics statement. Means we cannot create the energy, we cannot destroy the energy, but the energy can be transferred within the system one form to another form. So whatever the energy enter into the system has to come out. If it is not coming out, means there is a heat losses. So that indirectly it is saying that. So using this this first law of thermodynamics, so many practical applications are designed and understood their processes. For example, here it is mentioned few example in them: heat engines, refrigeration and air conditioning, chemical reactions, thermal power plants, and combustion process. We will see briefly about how this first law of thermodynamics is useful to design the heat engines. Actually, heat engine, using the heat engine, we can see this is a steam engine, this is a heat engine vehicle. Though in heat engine, the heat energy converted into mechanical energy. So whatever the heat energy enter into the system has to come out as a mechanical energy. If it is not coming out, 100% heat energy has to come out as a mechanical energy or mechanical work. If it's not coming out, means there are some losses. So this, the first law of thermodynamics says that whatever the heat energy entering into a system, that has to come out as a work energy. If it is not coming, there are some losses. So what are those losses? How to design your engine such a way that to minimize those losses? So this thermodynamics, first law of thermodynamics, is helpful to design the steam engine and heat engines. Next one is the refrigeration and air conditioning. So refrigeration means the reducing the temperature when it is compared to the room temperature. Okay, so means the heat here in the refrigeration and air conditioning, the heat is transferring from the low temperature to high temperature. Means, okay, so now the whatever the heat is transferred, whatever the work is done to transfer low energy or energy heat into high energy high temperature, then it has to be equal. Means whatever the work is done to transfer the low temperature heat to high temperature, so that has to be, both has to be equal. Means so this first law of thermodynamics helps to design this work, whatever the work we have done, amount of work we have done, that has to be equal to the transfer of energy from the low temperature to high temperature. If it is not done, then we need to design the system such a way that the amount of work is equal to amount of heat transfer. Okay, so in that way it is useful. Next one, chemical reactions. So chemical in a chemical reaction, it helps to understand the energy changes associated with the chemical reaction, including heat transfer and work done. So when the chemical reaction is done, the heat is released or absorbed. Okay, so means whatever the to understand the reaction mechanism or reaction phenomena, the thermodynamics will help. Next to thermal power plants. The first law of thermodynamics will help in analyzing the efficiency of these power plants and optimizing their performance. So here is what is happening in thermal power plants. The heat energy is converted into electrical energy. So heat energy converted into electrical energy. Whatever the heat is transferred to the system, that has transferred to electrical energy. Means only heat can be we cannot create this energy, we cannot destroy the energy according to first law of thermodynamics. We can transfer it. This is also transferring also from heat energy to the electrical energy. It has to be 100%. If it is not happening 100%, that means there are some losses. So how do I design the thermal power plant such a way that so that the losses are minimum and losses are minimum, efficiency is more. So to design the thermal power plants, the first law of thermodynamics plays a huge role. Next one, combustion process. The first law is crucial in analyzing the combustion process, such as those occurring in engines and furnaces. So the hydrocarbons, when the combustion is taking place in the heat engines, they will burst. Okay. So it helps in understanding the energy release during the combustion and associated changes in temperature, pressure, and volume. So whatever the combustion process, for example, hydrocarbon is reacting with oxygen and releasing the carbon dioxide, water, and heat and light. Whatever the input is equal to output. So this reaction, the hydrocarbon plus oxygen, the amount of mass is entered into the system, means the energy entered into the system has to be equal to the out. So if it is not like that, then we need to design the system or device such a way that the whatever the from this reaction inputs is equal to outputs. So with this completed the content are topics which are related to first of thermodynamics. Next we will see the content which are related to second law of thermodynamics. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.